This is Raymond Monroe with the Steel Founders Society. This seminar is directed at additive manufacturing and how steel castings interact with additive technologies. I'm really excited about this discussion because additive manufacturing is one of the big transformational technologies that will make steel castings a much more fundamental manufacturing process as we move into the future. Additive is one of the most exciting enabling technologies for steel casting, and we hope that we can communicate how to enable our customers and our users to use additive manufacturing to gain the maximum benefit, whether they use a casting or an additive metal part. What is additive manufacturing? It's really pretty straightforward. You have to take a 3D model. So you need a computer model of the component or the part you want to make, and then you break it down into layers, and each layer then can be printed with a 3D printer. And so now some people, instead of saying additive manufacturing, are using 3D printing as the most useful way of talking about it. It's the hot new technology topic, and so it's really a pretty exciting area. And of course, especially in the universities and even in the maker movement, there are plenty of people who are buying their own small $300, $500, $700 plastic printer and making parts. Metal casting was one of the original users of additive technology. We're not Johnny come lately. We're actually among some of the very first people who used additive technology. We used it in SLA to make plastic parts that could be turned directly into investment casting. We used it to print or cut layers of paper and make patterns out of it. You can see that we had a seminar back in 1999 with Jim Conley talking about fast freeform fabrication as a way of moving forward the technology of additive in steel casting technology. So to give you some background why Steel Founders Society and Additive, steel casting producers, we're one of the most, if more advanced, if not the most advanced users of solid models and process modeling. Most steel foundries have solidification modeling, and they use that to manage their process and to ensure the quality. We were also early adopters of additive because our solidification model already used STL files, and so we already had the infrastructure to move those over and make investment casting patterns, prototype tools, or printed sand molds or ceramic molds and cores. Now, personally, I've been engaged in technology and advanced manufacturing steel castings for over 40 years. I've been a member of the Joint Defense Manufacturing Technology Panel, Metal Subpanel, as an industrial advisor for over 20 years. This is the panel that would review all of the DoD-related advances in additive manufacturing. And so I've been involved from the very beginning of the development and transition into use within the Department of Defense. And I was involved with Ralph Resnick, who was the first runner of America Makes, when he brought it with the X1, the printed mold technology, over to the US. And so we've been involved with additive from the very beginning. And so I thought I'd go through briefly some of the advantages and then talk about some of the issues. I tried to give you just a flavor of how additive and steel castings interact. Now, what makes a part attractive for additive manufacturing? If I can put several parts together that I used to have to make independently, if I can put more functionality in the part, if I can reduce the weight of the part, these are the primary benefits. Less weight is less attractive, although for expensive materials, it can be important. One of the big advantages are these first two: lead time reduction. If I've had to make tooling or do process development or acquire material, with additive manufacturing, I may be able to reduce the lead times dramatically. And if I only have a small amount of production or I have obsolete things, I can reduce my inventory of both tooling and parts if I can manufacture them rapidly with an additive manufacturing. These two are not nearly as clear. Supplier risk, additive has the same supply chain kinds of issues as any other manufacturing, so it's not clear that and in fact, oftentimes when you have a critical part, you have to qualify both the process, the machine, and the supplier. So you may have less of a supplier redundancy than you do with other manufacturing methods. Additive, one of the big benefits is it gives design freedom. Traditionally, mechanical engineers and other design engineers oftentimes put things together the way kids put Legos together. They have standard mill products that they cut into pieces and then weld or bolt together. With additive, I can have complete geometric freedom. So these are some example geometries where you wouldn't ordinarily make any of these geometries out of fabricated parts. Some of these aren't bad for fabrications, but they're not attractive. But you can make all these clever geometries to achieve certain design characteristics. So traditional designs often rely on standard material forms. One of the key historic attributes of castings is this design freedom. It's hard to imagine how you can get the internal passages and the complex material shapes for engines, heads, and blocks if you didn't have casting technology available. Additive early on was called fast freeform fabrication, talking about its geometric thing. And of course, all techniques that have internal cavities, whether it's casting or additive, you still have to be able to look in that hole, get rid of the material, and inspect and make sure you've made the part. One of the biggest benefits is castings. One of our biggest challenges historically has been to make the first casting, I have to make a tool. And the time and expense of making the tool may take so much effort and so much expense that you can fabricate or machine 5 test articles in the money and time it takes me to make the tool. So making that first tool took time and money. Not only that, it meant that you already had committed to a particular design concept and had limited opportunity for improving and changing it. And so additive actually accelerates the development dramatically. So instead of 8 weeks to get a tool, I can give you a part in 3 weeks. But it's better than that. I can not only give you a casting in 3 weeks, I can actually give you 4 different castings for the same part. So if you have alternative design concepts, additive manufacturing, additive printing of molds or cores allows me to make 4 different concepts without ever committing to a tooling. And that allows you to try some really crazy idea that you never would have tried before because you couldn't afford the tooling and the time, because it can be in parallel with the more traditional and safer designs. So this is huge. I imagine that everybody that's creative and innovative design is going to need additive manufacturing to accelerate their design process, and castings enable that by giving you qualified metal parts with good, reliable properties in alternative design paths that let you maximize the creativity and innovation of your design process. If I look, additive allows for toolless production. So all of these tens of thousands of obsolete patterns, if we had solid models and we could print them, we could eliminate all of this sunk investment and this ongoing storage cost and maintenance cost. But the challenges include most of the time in traditional and obsolete parts, we don't have a normative, an authoritative solid models. Oftentimes the parts are compliant with the existing tooling, but not with the actual drawings. And I may have a higher part cost and limited production by using printed molds. But moving into the future, we certainly can see that obsolete and old, where you're out of production, limited production items, whether upfront or afterwards, will be made using this technology. We can print sand molds, and that's the huge benefit. I can get the additive benefits from printing the mold, and then I can get the metal performance out of pouring the mold with a reliable casting alloy. And you can see we can make really complex molds. One of the best benefits, if we only need 1 or 2, we don't have to recreate the tooling, the expensive tooling. We can make the 2 directly if we can get the solid model. One of the biggest benefits right now is if I have complex parts like impellers that have multiple pieces, I can actually print a core faster and cheaper than I can make the core or make the die, and that saves me money directly. But it's better than that. I actually reduce the dimensional variabilities, because instead of assembling several cores, I can make it as a single piece mold core combination and get much more repeatable and tighter tolerance parts. That's one of the big benefits the Air Force is seeing in printed ceramic cores, because these little cooling passages used to have to be drilled, and so they had to be perpendicular and they had to be round. Now, if I can print a ceramic core, I can positively locate both the cooling passages and the vent holes and know that they're going to be in the right place, and I can change the geometry. So this is huge, being able to control dimensions and geometry and location in a way that I never could with assembled molds and cores or other manufacturing technology. So you can see that there's really two fundamental concepts that make additive attractive. One is if I'm only making a few, then I can eliminate the tooling and the development costs and go straight from the solid model. Or if I have a part that's really complex, then being able to manufacture it with additive gives me both the complexity and the cycle time that I want with low cost and high performance. So what production process? I was delighted to find this because they recognize that printed sand molds, the X1 or the voxel jet process or the printing process, allows you to consider castings as one of your additive processes. The others, of course, are powder bedded or directed deposit. These are really welding techniques. Here you're welding, you're fusing or centering the powder onto the part. Here you're actually welding the part together. So one of the criticisms some additive people say is that when I make a casting, I use production welding to meet the quality requirements. But if I'm doing additive manufacturing, the whole part basically is made with fusion welding type technologies. And so this is really the kinds of processes you can get. And here's a picture of them. And you can see in this picture that most of these have really limited sizes compared to castings. And you have limited alloys. And so it really is a challenge to make the maximum flexibility in part without having castings as one of your opportunities. If you look at the materials, oftentimes you may want a bronze alloy, but the only thing you can print is a stainless steel. In castings, we can make the whole range of alloys. In additive, you have to depend on the powders that are available, the machines that are available, and the properties that you need. And so there are some real limitations. Now, many of those limitations will go away. Many of the limitations of performance will go away. But at this moment in time, there are some real challenges of being able to fully utilize additive metal printing. One of the challenges is that if, depending on the orientation, horizontal, vertical, different angles, different post-processing, you can get a wide range of properties. So this is for 17.4, a high-strength stainless steel that's used in structural applications. And you can see, depending on the orientation, my yield strength can be half of the yield strength of the mill product, and my ductility can be well less than half. Now, that's not necessary. It's not always common. But because of that, there are none that I'm aware of standard processes with standard properties. So virtually every critical component in additive manufacturing where you're metal printing has to be qualified based on the source, the machine it's made on and its process, and part verification or part qualification. And so that's a real challenge. And many of those problems go away because metal casting is a well-known technology. Now, one of the things that people will talk about is yield, because at least notionally, you get 100% yield because you can reuse the powder you didn't fuse. But oftentimes in additive, you need a support structure in order to make these complex geometries. And so the yield of a casting, which is limited by the plumbing system, the gating, and the risers, the yield on an additive part is limited by the support structures and the things you put on it to handle. One of the great benefits is many of the quality challenges and performance challenges of printed metal molds are similar to the challenges of getting optimal properties out of casting. And so, for example, additive routinely would use hot isostatic pressing to maximize their mechanical properties. We get the same benefit in castings by using hipping. So the infrastructure for design, for quality assurance, and for post-processing that's used for additive manufacturing will seamlessly provide benefits for steel castings. You can see this is hot isostatic pressing of the cast Xeron 100 material. The solution annealed material gives really nice impact properties, but the optimal impact properties come from hipping because you reduce the size and the quantity of small shrinkage pores and cavity. So if I look at a comparison, printed metal parts with additive are the newest and coolest technology. If you want young people to come through your facility, you want to show them your printed stuff. The VP of operations or marketing wants to come through and see your printed molds. But it requires source and part qualification. One of the huge benefits that we don't have in castings is you can make constitutionally graded material, so you can go from a hard surface to a tough and ductile center by changing the material as you build the part. And of course, the parts are limited by the machine size. In casting, you have an older, more mature process, which has both the advantage and disadvantage. The advantage of being well known and the process controllable. The disadvantage is it looks like old technology, and so it's not as exciting. You have design properties already available in a stable process. We can cast a wide range of alloys, the widest range of alloys actually of almost any process, and the properties may be limited by section size. So in printed mold, since it's a welding technique, no matter how thick the section gets, I get relatively uniform properties or lack of properties in direction based on the actual build schedule. In castings, because I'm limited by physics, when the part gets thick, the solidification rate is going to be slow and my mechanical properties may be different. So the benefits, as I see it, of additive are geometric freedom, not tied to existing material form, the ability to move directly from a 3D design solid model to prototype and production without the cost, time, or need for tooling or process development, the capability of considering alternative and design paths, and the ability to produce limited quantity obsolete parts or complex parts with no existing tooling. So hopefully you found this useful. If you want more information, and this is my contact information, I was able to find a lot of material on evaluating the processes and limits of additive manufacturing, not castings, online. If you'd like some of that material, if you send me an email, I'm happy to share it with you. It was available on the web. And if you have any questions about the utilization of additive techniques in steel casting, or you need contacts that America makes, or want information about additive per se, I'm happy to try and connect you with the smartest people that can give you the most advanced information.